Kovac Center is a defense manufacturing company based in Valjevo, Serbia, specializing in the design, production, and assembly of weapons, ammunition, and missile systems. The company is known for its ability to supply high-quality products to the Serbian military and export to many other countries. With a team of experienced engineers and scientists, Kovac Center has become an icon in the Balkan defense industry. Engineers and scientists conduct in-depth research on technical requirements, desired performance, and international standards. They then use specialized software to create detailed 3D models of the product, from which they analyze the structure, dynamics, and other factors. Determine the type of missile, surface-to-surface, air-to-air, air defense. Break down the design into components such as guidance systems, warheads, engines, and frames. Simulate the trajectory, aerodynamics, and performance in a real environment. The next step is to select materials and process. The rocket frame is made of aluminum alloy or composite to ensure durability and lightness. The engine is made of high-temperature and pressure-resistant materials. Finally, the guidance system and sensors and electronics are manufactured in a clean room environment. The main components include solid fuel engine, uses a mixture of fuel and oxidizer poured into the combustion chamber to create stable thrust. Warhead designed to ensure accurate explosion when hitting the target or according to programming. Guidance system uses GPS, radar, or infrared sensors for navigation. Next, the rocket is assembled by Kovac in the order of the engine stage, and then the warhead. The engine stages are assembled to ensure accurate thrust and separation. The warhead is mounted and connected to the electronic system. The engine is activated under fixed conditions to test the thrust. Test the trajectory and operating conditions of the rocket. The rocket is launched at the test site to evaluate performance. All Kovac Center products meet international standards and are designed to operate effectively in all harsh conditions. HK Krušik is one of the leading manufacturers in Serbia of missiles and defense weapons, with a rich product portfolio serving various military purposes. Krušik's missile products are known for their reliability, efficiency, and are widely used in both defensive and offensive combat environments. Here is an overview of the company's current missile types. 1. Anti-tank missiles. Krušik's anti-tank missiles are designed to destroy armored targets such as tanks, armored vehicles, and fortified structures. There are two prominent types of anti-tank missiles. The first is the M79 OSC. This is an unguided anti-tank system using a shoulder-fired launcher. Highly effective in destroying tanks and fortifications thanks to the heat, high-explosive anti-tank warhead. It has a firing range of 400 to 600 meters, armor penetration capacity of up to 400 millimeters of homogeneous steel, RHA. The second is the M90 Strasition Hornet. This is a semi-automatic anti-tank guided missile, SACLOS, suitable for destroying mobile or fortified targets from a distance. It has a range of 2.5 to 3 kilometers, armor penetration capacity, over 600 millimeters after ERA, explosive reactive armor. 2. Air defense missiles, MANPADS. Krušik's air defense missile systems are designed to protect against aircraft, helicopters, and UAVs. There are two prominent types of air defense missiles. The first is the Mistral. This is a shoulder-fired infrared-guided missile produced under license in cooperation with MBDA, France, used to destroy low-flying aircraft or helicopters. It has a range of 6 kilometers. The second is the RLNIC. This is a short-range missile with an improved infrared guidance system, used in fixed and mobile air defense systems. It has a range of 5 to 8 kilometers. Mach 1. Multi-role missiles. Crucix multi-role missiles are capable of destroying both ground and air targets, depending on the configuration. Notable is the R-400 missile, which can be equipped on unmanned aerial vehicles, UAVs, or ground vehicles, with a range of 10 kilometers. 4. Unguided missiles, rockets. This type of missile is commonly used in ground and air-to-ground combat, with multiple launch systems, MLRS. There are two prominent types, 122mm Grad rockets and 128mm Playman rockets. 5. Guided missiles. This type focuses on fixed or mobile targets at long distances, often deployed from ground launchers or warships. A typical example of this missile model is the ALAS, Advanced Light Attack System. This is an advanced guided missile, using electro-optical cameras to find and destroy targets, integrated in ground attack or coastal defense systems. Its range is up to 25 kilometers. The guidance system combines GPS and live video. With experience in advanced technology, Crucix products not only meet domestic defense needs, but are also the first choice for many armies around the world. Let's take a look at the missile production process at HK Crucix. Every missile product starts with an idea and specific technical requirements. Scientists and engineers work closely with the customer to determine the exact specifications such as range, accuracy, warhead type, and maneuverability, simulate the missile's performance in different environmental conditions such as temperature, pressure, and wind speed. The missile's shell is usually made of light but very strong alloys to ensure rigidity and heat resistance. The manufacturing process includes cutting, bending, welding, and surface machining. The rocket engine is the heart of the system. Crucix uses different types of fuel, from solid to liquid fuel, depending on the requirements of each type of missile. The engine manufacturing process includes the fabrication of the combustion chamber, nozzle, and control system. The guidance system includes sensors, computers, and other electronics. These components are manufactured with high precision to ensure that the missile reaches its target accurately. The type of warhead will depend on the intended use of the missile. Crucix produces a variety of warheads, from high explosive to penetrator warheads. Warheads are designed to achieve high penetration or create maximum blast waves. The explosive is compressed into the warhead by an automatic device, ensuring compression and safety. Warhead uses a heat and pressure-resistant shell to protect the explosive during launch and impact. The engine is machined from a high-temperature alloy to ensure stable engine operation. Solid fuel is poured into the combustion chamber using a special casting process, which optimizes thrust. The nozzle is designed to optimize thrust direction, improving flight trajectory. Sensors such as GPS, radar, or infrared are integrated to ensure that the missile follows the target. The microprocessor is programmed to calculate the flight trajectory and adjust the direction of travel. Crucix uses CNC machines to machine the missile frame with high precision. The surface is coated with anti-oxidation and high-temperature protection, ensuring the missile operates stably in all conditions. The engine stages are attached together to ensure strong thrust and precise stage separation. The warhead is connected to the electronic and mechanical systems for activation when necessary. The guidance system is connected to the entire system to ensure the missile can self-orient. All components are thoroughly tested before assembly to ensure they meet the highest quality standards. After assembly, the missile is comprehensively tested to ensure all systems are working properly. The rocket engine is tested on a static launch pad to evaluate performance and reliability. The missile is launched to test the guidance, control systems, and other flight parameters. Crucix has a strict quality control system to ensure that every product meets the standards. Before delivery, the rocket is thoroughly tested again to ensure it meets all customer requirements. Advanced 3D printing technology and artificial intelligence are applied by Crucix to the rocket production process to optimize the design and production process. Rocket production is a complex process that requires a combination of science, technology, and high engineering. Crucix prides itself on its ability to produce high-quality rocket products that meet the most stringent customer requirements. United Launch Alliance, ULA, is a joint venture between two American aerospace giants, Lockheed Martin and Boeing. Founded in 2006, ULA specializes in manufacturing and launching rockets for scientific, commercial, and military missions. ULA's famous rocket lines such as Atlas V, Delta IV, and the upcoming Vulcan Centaur are highly regarded for their reliability, outstanding performance, and ability to operate in a variety of harsh environments. The rocket manufacturing process at ULA is a complex process that requires high precision and strict adherence to quality standards. Below is a detailed summary of each stage. 1. Research and design, R&D. Determine the rocket's mission, whether it is to launch satellites, carry cargo to the International Space Station, or conduct interplanetary scientific missions. Use advanced design software to create detailed drawings, including components such as the rocket body, engine, and guidance system. Simulate aerodynamic factors, loads, temperatures, and pressures under real conditions to optimize the design. Create small models or test prototypes for each part to test and refine. 2. Material selection and processing. There are three main groups of materials. First is ultralight aluminum alloy, used to produce the rocket body, ensuring high load-bearing capacity but still maintaining lightweight. Second is carbon composite, used for parts that need to withstand large forces but require weight reduction, such as solid fuel engine casing. Finally is titanium, used for important parts with high heat resistance and corrosion resistance. 3. Processing of main parts. The rocket body is rotating friction welding. This advanced technology helps weld aluminum or composite plates with high precision without reducing material quality. Small parts are CNC machined to micron precision. Propulsion system uses special alloys resistant to high temperatures and extreme pressures. Liquid fuel pump turbines are meticulously machined for maximum efficiency. Guidance system has acceleration, pressure, and temperature sensors assembled in a clean room to ensure accuracy. Computer system, designed to process data from sensors and control the engine in real time. 4. Rocket assembly. The main booster stage, containing the engine and fuel, is assembled first. Fuel lines and valve systems are tested to ensure no leaks. The upper stage contains the smaller engines and trajectory guidance equipment. Electronic systems are connected to ensure compatibility with the main booster stage. Locking/separation mechanisms are integrated to ensure the rocket stages can separate accurately during flight. 5. Quality control and testing. The engine is mounted and fired to test thrust, fuel burn, and stability. All systems are tested under conditions that simulate real-life temperatures, pressures, and vibrations. 6. Transport and launch preparation. The rocket is transported by specialized ships to launch sites such as Cape Canaveral, Florida, or Vandenberg, California. The rocket is erected and mounted on the launch pad. The fuel and electrical systems are connected to the ground infrastructure. A series of final tests are performed to ensure all systems are working in sync. 7. Rocket launch. The rocket is loaded with liquid fuels such as LOX, liquid oxygen, and RP1, refined kerosene. A countdown procedure checks all systems one last time before engine ignition. The main stage engine is ignited, sending the rocket off the launch pad and into orbit. With over 150 successful launches in a row, ULA is the first choice for critical missions. ULA rockets are optimized to launch payloads to a variety of orbits.